Okay, our first chapter is called Functions and Limits. And in this chapter, we are going to cover the 6 sections in there, but we are going to switch up the order here at the end a little bit. We'll start out with section 1.1, which is entitled Functions and Their Representations. And we have a couple of definitions here to start off. First one is a definition of a function. Should have seen this in college algebra. Basically, a function is a rule that takes some number, x, in some set D, and sends it to exactly one other number called f of x in some other set E. We'll have visualizations of all this in just a second. The set D from this example, where your x's come from, is called the domain of the function. And it is the set of values which the function may be evaluated at, or all the allowable inputs of the function. So everything that can go into the function is called its domain. Close this out as I go. All right, the range of a function, for every x that you plug in from the domain, the function sends that x to exactly one value, f of x. All of the things that come out of the function is called the range of the function. So the range is all the outputs. The independent variable is the variable which takes on the values from the domain. So that's usually the x in the equation, and we call that the independent variable. The other variable, which is usually y, is called the dependent variable, and that's the next definition. So the output of the function is your dependent variable. All right, let's get to the graph of a function here. All right, the graph of a function is the visual representation of all the inputs and all their corresponding outputs. It is a set of ordered pairs like this. So let me explain what this is. The braces on the end here tell you that this is a set. It's the set of all ordered pairs. So this is like a point. It's like the point 2, 5 or something like that. This ordered pair, you take all of the ordered pairs for every x within the domain of the function, and that is going to represent basically the graph, all those points graphed. So we have an example here finally. If I give you something like graph y equals this function, which is negative x cubed minus x squared, by plotting 5 points, what you do is you take a t-table here, you create some values, some inputs. These are values out of your domain, -2, -1, 0, 1, 2. You plug those into the function, so you replace what's going on here? You replace your x value here in the function with -2. -2, you evaluate, you get 4. If you plug in -1, you get 0. If you plug in 0 into this, you get 0. If you plug in 1, you get -2. And if you plug in 2, you get 12. So what you do is you plot all these ordered pairs, like -2, 4. You would go to the left 2, 1, 2, and up 4. Boom. Plot that point. If you do all 5 of these points, you get these points on the graph. So that gives you some idea of what the function looks like. Now the next example, what I do is I take that same 5 points we just had, and this little interactive module here will allow you to add more points. So what if I did 25 points instead of 5? So if I did 25, here's a better idea of what that graph looks like. If I do 50 points, here's 100 points plugged in. And now I have a real good idea of what that function looks like. So if I click on here, show function, it's actually going to show me the real graph function in the red. So the more points you put in, the closer you get to the true function there. All right. Now, this is one of the most important concepts we need to make sure we understand, is that f of x, that's the value of the function, is the height of the function at the value x. So if I plug in a value x of, let's say, -6 here, if I plug in -6, it goes into the function spits out -9.6, so that's way down here. I can take this slider and I start moving my x value around. So you can see now I'm at -5.4. If I plug in -5.4, I get -4.8. So the output, the f of x, is how high this function is. Now, of course, it's negative, which means it's below the x-axis. If I move my x value over somewhere here, now if I plug in -2.8, I get a height of the function of 3.4. So the main idea here is that f of x, the value of the function, is blue, is always going to be how high your function is at that value of x. So you can just drag this along and see how that works out. Okay, next, the vertical line test. To test if a graph represents a function, that is to say y is a function of x, we apply the vertical line test. Basically, the vertical line test says if any vertical line intersects the graph in more than one point, then the graph is not a function. So as you look at this graph, this blue graph here, it's actually a sine wave. If I drag this across, you can see I'm trying to see if this vertical line hits the graph more than once or not. So it's hitting it in only one spot. So it's a green line telling me everything's good. This is a function. That's a function everywhere in here. Now, if I switch to a different type of graph like this, you can see I've got this sideways parabola. I'm doing the vertical line test over here. Right now, everything's okay, because to be a function, you just can't hit more than one time. Here, I'm not hitting at all. That's all right. It's when I get over to this side, see my line turned red, that's telling me, look, I'm hitting it in two spots here. So this is not a function, or you could say that y is not a function of x here in this graph. So vertical line test, very useful. All right, next thing, piecewise functions. A piecewise function is a function that is defined to be different functions on different ranges of the domain. Okay, what does that mean? Well, here's an example. Here I have a function, f of x. It's equal to x squared plus 1 if x is less than or equal to 1, and it's negative x squared plus 2 if x is bigger than 1. So what you want to do is imagine a line here. Here's the critical value of x. When x is less than or equal to 1, so here's 1 for x. Everything to the left of that, that's less than or equal to it. The function is this one, x squared plus 1, which is a parabola that's been shifted up 1. So you can see here's my little parabola, opens up, and then I get all the way to 1. When I'm at 1, I actually am at the value of 2. So at 1, my x value plugged in to be 1 evaluates to be 2. If I plug in anything bigger than 1, then I'm going to be this parabola, which is a negative parabola, which means it opens down. So this parabola actually does something like this, curves, but I can only draw it whenever x is bigger than 1. So I start here, and I draw down the rest of the graph. So this is a piecewise function. It's two different functions on two different parts of its domain. These are going to be very useful to us as we move forward. All right. Definition. Intervals where a function is positive, negative, and 0. So a function is said to be positive on an interval I if the function is greater than 0 there. Remember, f of x is the height of the function. So if the height of the function is greater than 0 or positive, then it's said to be the function said to be positive there. If the height of the function is negative or below the x-axis, then we call it negative on that interval. And if the function is 0 on some interval, then it's said to be 0 there. Here's an example. So right now we have a function, x cubed minus 4x. You can see it comes up, back down, back up. Let's figure out where the following function is positive, negative, and 0. So first let's start with positive. Positive would be everywhere where the function is above the x-axis, which would be right here in this area. Then from here up, so I'm going to click here, show positive. You can see here, that's where it's positive, and that's where it's positive. The answer is the x values that you would plug in to make the function positive. So notice if I plug any x value in between here and here, my function, my outputs will be above the x-axis. So how do I say everything between here and here? I say from negative to 0. Also, from 2 on to infinity, my graph is above the x-axis. So I say unioned with to infinity. Now, where is it negative? Well, that's going to be where it's below the x-axis, which happens here and then over here. So how do I represent my answer? Well, everything that gives me a negative value, I'm looking a negative value of the function. I'm looking for the x values that do that, which would be everything on this red line. If I plug in an x here, spits out an answer down here below the x-axis. So how do you say all this over here? You say negative infinity to negative 2. That'll bring you all the way out this line forever to the left, all the way to negative 2. Then from 0 to 2, I'm below the x-axis also. And then where is the function equal to 0? Well, there's actually only 3 points, not intervals, where the function is 0. So I'd say that at the The places that my function is 0 is at the point -2, the point 0, and the point 2. So notice what I use here is I use braces around these values. The braces, again, represent a set of points. So there are only 3 values where your function is 0. Just make sure you understand the difference between using a set of braces and a set of parentheses. Parentheses represents everything between the braces, excuse me, just mean those 3 points in this case. All right, next definition, where a function is increasing, decreasing, and constant. So a function is said to be increasing on an interval if f of x sub 1 is less than f of x sub 2 whenever x1 is less than x2. All right, what the heck does that mean? And then decreasing means this, and then constant means this. So really, let's get to a picture. I think that we'll be able to figure this out. I'm going to leave that note up so we can refer back to it. So here's an example of an increasing function. So what I'd like to do is bring it so you can see this. I have 2 values of x that I'm plugging in, x1 and x2. Notice that x1 is -4.5. That value is less than -3.5, which is x2. So I have two values of x1 and x2 right here. So right now, if you go up here, my x1 is less than x2 because it's to the left of it. Now, what's happening with the function? The function's value at x1 down here, -8.9, is less than the function's value here, -4.1. So this points to the left of this one, and this point is below this one. And notice that that's going to happen the entire time I do this. My point to the left is always below the point to the right. And so what you get is this idea that if this is true, your function is increasing. So I'm going to draw a little arrow just so you know, like if this is a roller coaster and you're riding this roller coaster from left to right, you're going to be going up the entire time. The entire time you are increasing. Now again, that's from left to right. You're increasing. All right, let's contrast that with the decreasing function. The only difference with the decreasing function is that when your x1 is less than x2, same with this, it's flipped over here. Now your first point's bigger than your second one. So let's see. So notice, again, my x1 is less than x2 because it's to the left, but now my function's value at the first point is higher than the second point. So this point will always stay above this one. So as I move from left to right, it's always below. And so I get this idea that as I move from left to right, my function is decreasing. There's the little arrow to kind of represent that. You're going down the entire time. All right, let's contrast that now with a constant function. Constant function, go back up to the definition here, means that the function's values are always equal on that interval, no matter what. So when I come here to a constant function, my x1 is to the left of x2, but my function's values are always remaining the same. So what you get is just basically a flat line. And if you do an arrow, you can see it's just going to stay straight the whole time, constant. All right. Let's now look at determining where a function is increasing, decreasing, and constant. So back to this example, we already did this earlier. We were talking about where it was positive and where it was negative and things like that. But now I want to talk about where is the function up, increasing, decreasing. Let me change this real quick. This might happen a few times here. Decreasing and constant. All right, sorry about that. Okay, so where's the function increasing, decreasing, and constant? Well, if we're moving from left to right, you can see that we're going up here. And so we'd be increasing over here. And then when we get to the top right here, we start decreasing and going down until we get to the bottom. And then again, we start increasing again. So let's show the increasing intervals right here. Everything here I'm increasing, and then from here up I'm increasing. And again, our answer is the x values that where it's the x values in the domain that cause your function to increase. So I want everything from about this point right here to the left. That'll be my answer. But how do I say that? Well, from negative infinity all the way up to this point here. And we're not going to look at how I got this point yet. That's part of what this class is about. But I just put it here for you at negative 2 over root 3. That's exactly this point. That's where I stop increasing. Then, again, from this point on forever, right, on my x-axis, I'm increasing. So what's this point? My x value is 2 over root 3. Again, don't worry about where I got that. And then it increases over there forever. Now, where's it decreasing? In here, right? So when I decrease, it's right in there. So my answer is the interval right in here. And again, that's going to be from that same negative 2 over root 3 all the way to 2 over root 3. So that's where my function is decreasing. And then constant, I don't ever have this function flatten out anywhere. So we use this symbol right here. It represents the empty set, which means there's no answer. So there's no place that this function is constant. All right. Get to the next example. Determining the domain of the function algebraically. So these will be done in class, but what we want to do is we want to figure out the implied domain. So what we're determining is what values of x can and cannot go into these functions. And we'll do that in class. All right. Now, this one we will also do in class. This is about trying to take some sort of geometric shapes and trying to come up with some equation that relates one aspect of the shape to another. So we'll be doing these in class. Like I want to take the area of a circle and determine that as a function of its diameter. So how is the area of a circle related to its diameter? The second one, how is the volume of a cube related to its surface area? And then the third one, surface area of a sphere, how is it connected to its volume? So we'll do all those in class. That's 1-1, and we'll also be working on the homework assignments in class for that section.